Okay, let's summarize what we got. So we looked at the following model. We have a source which produces two sequences, xn and yn, like in distributed source coding, depending on a joint random variable xy. And the sequence yn directly goes to the decoder. The sequence xn goes to an encoder, and he wants to compress the sequence to some index w. The receiver receives yn and the index w, perhaps as a binary string or something like this. That's the reason why we measure the logarithm to the basis 2. The decoder sees both the w and the yn, and his goal is to produce an output sequence x hat of n in such a way that the distortion, the expected distortion between xn and x hat of n is lesser equal d. And then we use some tricks to get a rate region, or to get a rate which is possible. The idea is, first, we use random coding. Second, we use binning. And third, we use an auxiliary channel U to decouple somehow the output of the source and the coding, or also to give some more possibilities, because U is normally bigger than X. Then our result is that we have to take the minimum over all possible channels, such that the expected distortion is lesser equal than D, such that the mutual information between X and U minus the mutual information between Y and U is minimized. And for the converse, we used really the idea, we start always in the same way, you should know this. Then we use again that the rate function is convex, also like we did in the last proof. And we use the data processing lemma or inequality, and we use Fanus inequality. And with these tools, we can show that we have really this rate here, and it's optimal. That is the result for rate distortion with site information.